you know that we are studying rational number and irrational numbers, rational number, irrational numbers, and also rational numbers and theorem based questions related to it. So we are going to solve. So here, so first theorems we have to prove that. So let's PV theorem. So okay, theorem here is given that. So let's P be the prime number. One. Let's P be the prime number. Okay, let's P be the prime numbers, and A be the positive integers, and small a be the positive integers. Okay, positive integers. B, small b is the positive integers. If p divides a square, if p divides a squares, then p divides a, then p divides a. Okay, so p divides a. These are the questions. Some theorems is given here. We write here as a statement given is here that's let's be the prime number, and a b, let's p be the prime number, and a be the positive integers, a be the positive integers, and p divides a square. Then we have to prove that p divided, prove that p divides a. We have to prove that so p divides a. Now proof. Okay, what we will do here, so to prove, so we know that every positive integer can be, we know that every positive integers can be expressed. Okay, every positive integer can be expressed as a product of prime, as a product of prime. Okay, as a product of primes, we know that it's let's say a is equal to, so let's a is equal to p1 p2 p3, got it, p1 p2 p1 p2 pn, and also we know that p is equal to a is equal to, and where p1 p2 pt, where p1 p2 pn is, where p1 p2 p's are primes, the prime, not necessarily distinct. Okay, not necessarily distinct. Then so we can write here, so that a square is equal to p1 p2 pn and p1 P2 Pn. But it's product of the two numbers as we have mentioned here. So a square is equal to, so a square is equal to P1 P2 P square Pn square. But it's, as we know that Pn square. So now since P divides a square, now since P divides a square, then what we will do here, if P divides a square, then P is a prime factor of a square. Then P is the prime factor of a square. P is the prime factors of a square. So P is one of, so P is one of P1 P2 Pn, but it's one of P1 P2 Pt. Since by using the fundamental theorem of mathematics, since using the fundamental theorem of arithmetics, the only prime factor of a square is equal to P1 P2 Pn. Okay, always be only prime factor of series. So P divides A, since A is equal to P1 P2 Pn, what it's, so P divides A, P divide A, P divides A, then P divides A square, then P divides A square. This is the situations we have solved the P divides A squares, and again if we solve these questions, so hence it should be proved. Hence it proved. Okay, these are the proofs I have done here with a systematic way. I hope that you understood these questions similarly. Got it? Now we will discuss about other types of the questions that's related to the primes and composite numbers here, and some questions related to it, so that we can solve another types of the questions also. Okay, so here is the another questions, how we will express it. So we will take and the proofs on the basis of these theorems, some questions related to it. Here is the questions. Example, with the help of example, we will try to solve the questions. Theorem to prove that under 2 is irrational numbers. Questions. Or you can say that theorem proof that under 2 is an irrational number. Okay, we have to prove that under 2 is an irrational number. So what's let's assume that assume that under root 2 is a rational number. Suppose that under root 2 is a rational number, then it will be in form of p by q, where q is not equal to 0. Q is not equal to 0. So rb by q we can also write here, rb by q, and q is not equal to 0. So if we a by b, so we are taking a by b, so a by b, where b is not equal to 0 because it's a denominators. Then so it's again, let's a and b are, let's a and b are no common factor other than 1. Okay, other than 1. So under root 2 is equal to a by b. What is under root 2 is equal to a by b, where a and b are prime integers, co-prime integers, where a and b are co-prime integer. Okay, co-prime integers. So what we will do here is co-prime integers on squaring both sides, we get squaring both sides, we get under 2 square is equal to a by b square is equal to 2 is equal to a square 1 b square is equal to b square to a square. We can write like this, but it's a square to b square is equal to a square equation 1. Suppose that it's a equation 1. So 2 divides a square, 2 divides a, then 2 divides a square and 2 divide a. But it's why? Because theorem first. Theorem 1, as we have told here before, that theorem 1. So then a can be written as, so a can be written as, a can be written as 2m, where m is integers. M is integers. On putting is equal to 2m in equation 1, is equal to 2m in equation 1. Here is equation 1. So 2b square is equal to 2m square is equal to, we can say that 4m square. 2b square is equal to 4m square. Got it? So 2b square is equal to 4m square. So b square is equal to m. So b square is equal to 2m. 2m square. B square is equal to 2m square. Then 2 divides b square, 2 divides b. Then 2 divides b square and 2 divides B. Got it? Theorem first. 2 is a common factor of A and B. Theorem 1 and 2 is common factor of M. 2 is common factor of and sorry B, A and B, A and B, small a and B integers. Okay, so but this contradict that the fact that but this contradict the fact that A and B have no common factor. A and B have no common factor other than 1. No common factor other than 1. The contradiction arises by assuming that contradiction arises by assuming that 2 is a rational number. That 2 is a that 2 is a rational number. So under root 2 is a rational number. Proved. We have proved these questions with the help of the previous theorems. First theorems, on the basis of first theorems we have proved the second theorems that under root 2 is a irrational numbers, but on the basis of assumptions that under root 2 is a rational. Okay, these features I have solved here, solved here, and I hope you will understood its solutions. Thank you very much. Okay, bye bye.